So question 5 related to the atomic physics. An iodine isotope is there, which is 131 and 53. It is emitting out beta and it turned into a xenon. State the number of each type of particle in a neutral atom of iodine. You can use the screen annotation to complete. So the nucleon number, the proton number will be 53. That's right. And it's a neutral atom 53. Then you take a difference, so it will be 78. That's correct. Then what happened? It emit out beta. What will be the equation for beta? Like example, we have iodine, which is 131 and 53. When it emit out beta, the nucleon number does not change, so it will remain 131. But what happened to proton number? The proton number increases by 1. This is the beta emission. The general equation for beta, the proton number increases by 1, nucleon number does not change. So the question is, state the symbol in nuclide notation for a xenon nucleus. So when iodine emit out beta, it will turn into a xenon. So we want to just write the symbol for a xenon. So it will be Xe, 131 and 54. So in part B of the same question, the background counts or background radiation of a radioactivity in the lab is 30 counts per minute. Like radiation other than the source are 30. A radioactive sample has a half-life of 50 minutes. Means after every 50 minutes, the radiation will become half of its original value. The sample is placed at a fixed distance from a detector, and the detector measured the initial counts from a sample as 310. On a figure 10.1, plot suitable points and draw a graph to show the count rate from a sample corrected for background as it change over time. So corrected for background means like we don't want to include a background. Other than background, we have to mention. So if the count rates other than like corrected from background means you don't need background, you need other than background. So like only from the source. Yeah, that's right. So we start with, so example, the detector reading was 310 that they mention here. And out of 310, they mention how many are there due to the surrounding the background 30. So if 30 are due to background, how many will be there from the source? Because total should be 310. So source radiation, that's right, 280 are from source. So source rate, we just have to plot a graph for source, not for background. So first we start, as you can see, like 10 boxes equals to 50. So each box is representing 5. This is 100, 100. This one is 150, not 100. 100 is there already. So this is 150. This is 250. Now, in the beginning, how many radiations are there from the source? So we have 280 radiation from source. So each box is representing 5. So this will be 290. This will be 280. So this is 280. Then first is 280. Then after half-life, the half-life of the source 50 minutes. So after 50 minutes, how many radiations are there from the source?
140.
So it will be 140. So from 50 on x, because after every half-life, the source radiation will become half. So we have 1, 2, 3, 4, because this looks 50. Yeah. So this is 50 and 140. So 50 and 140, this will be the second point. Then after another 50 minutes, because the half-life 50 minutes, so after another 50 minutes, the radiation will be 70. So means at 100, the radiation will be 70. Then after another half-life, minimum like you should have 4 points to get a clear Like time axis is 160, so maximum you can have 3 half-lives in 160, as 150 will be the last. So this will be 35. So at 150, this is 50, 45, 40, 35. Then you have to draw a freehand graph starting with the maximum. Like you can start with any of them, but join the points. So this will be the graph, the shape of the graph you will have for this question. You cannot draw this with a scale, the ruler, that is wrong, because this is not point to point. It's not a straight line. It's always an exponential decay or a curve. If the points appear very close, like there are certain, for half-life, for atomic physics, decay, it's always an exponential, a smooth line graph. For when two quantities are directly proportional, then try to draw a best fit straight line. Like voltage, current, with Ohm's law, this Hooke's law, force in extension. In that case, you will always have a straight line. The question 6 from atomic physics. Bismuth 214 is a radioactive with a half-life of 20 minutes. So after every 20 minutes, the sample will change half of its original value, the radioactive sample. A nuclide notation of a bismuth is shown. State the composition of a nucleus. Composition of a nucleus means like what nucleus consists of. How many neutrons and how many protons. Don't mention electron. Why? Because they only ask for nucleus. So it contains 83 protons. That's right. And you take a difference, 214 minus 83, so 131 neutrons. Okay. That will be the number of the neutrons present in the bismuth. The next part, it decay by beta emission. Like whenever a beta decay, nucleon number does not change, proton number increases by 1. So you can use a screen annotation to complete. The nucleon number does not change at all. And proton number increases by 1. The charge, it should be 0 minus 1. This is not 1, 0. It should be 0 and minus 1. That's 0, the nucleon number for electron. As I mentioned, if you remember about the particle, if it was alpha, write 4, 2, or you can also write helium as alpha. If it is beta, you will write 0 minus 1, or you will write electron 0 minus 1. And gamma, just the symbol, but no charge, no mass. And neutron, if neutron is also there, so 1 and 0. So remember these particles, their symbols. The count rate, from a sample of a bismuth 360, predict the count after 60 minutes. And they mention it has a half-life of 20 minutes. Like after every 20 minutes, the sample will change half of its original value. So we have to predict what will be the counts after 60 minutes. So right now, example, we have 360 counts. The half-life 20 minutes. After 20 minutes, what will the count rate? After 20 minutes?
180.
180, because after half-life. Then after another 20 minutes, like total 40, but after another 20 minutes, it will be
90.
90. Then after another 20 minutes as the half-life, and in this question, there is no background radiation mentioned, so we don't have to consider that background. So another, it will be 45. So how much time has passed? Like 3 half-lives are there, or 60 minutes. When 60 minutes will pass, the count rate will change from 360 to 45. So you have to show this, like there's no formula you have to use. You just have to show this working here in the space, and then write the final answer, which is 45. Like 3 half-lives are there in this duration, and these 3 half-lives will uh, take about like the change the radiation from 360 to 45. Then state 2, social, economic or environmental issues which are involved in a storage of a radioactive material for a very long half-life. Like if a radioactive material is having a very long half-life, like it remained radioactive for a very long time, what might be a social issues, what might be the economical issues or environmental issues. So first, what might be the social issues you can mention, like it might cause like fear is there for causing a cancer, or it might cause a cancer, or it might cause a mutation. The social issue, if you mention, or because of, yeah, less tourists will be there, or less people will be there at that position or visit. Even you mentioned like people will move away from that environment. That is also a social issue. You don't have to mention all because it state too social or economic or environmental. So yeah, you can, and what might be in economical issues might be there related to that. If you mention, you can mention you need like it will increase the cost because you have to store the radioactive sample for a very long time. So high cost for storage will be there, and reduction of tourism, that is also you can mention in. And what might be the environmental issues? Environmental issues means like it can also cause a mutation to the crop, or it can pollute the environment, like it can leak into the water supply. They may also can make it radioactive. So variable answers are there for this, like it's up to you what you want to write.